And our next speaker is the one and only Carle Pieters, who will be speaking to us today on the evolution of mature soils at Lunar Swirls.
This is a really fun session. Right away, I want to change people's mind about the character of swirls. Notice the title. It says Evolution of Mature Soils at Swirls. One of the key things I'm going to try to convince you of is that these are not immature surfaces. They're still very magnetized, but they're not immature. Okay, you've seen this. What you probably haven't noticed is up at the top I have not only a strip of Reiner Gamma, a small strip, and we'll come back to it, but also, for comparison, a swirl in the highlands, namely this Gerasimovich, which is, again, one of the strongest magnetic anomalies in the highlands, and they have similar swirly structures. These are the small scale, not the large scale as the main head of the Reiner Gamma. And I'm going to mostly talk about Reiner Gamma, so we'll stay consistent. Here is just a regular albedo image, high sun, very low shadows. If you look at low shadowed areas, you start seeing the topography, or more importantly, at Reiner Gamma, the lack of topography. And if you look at the DTM of the same area, there is no topography associated with these wonderful albedo features. You can see the Marius Hills up there too, so it's a wonderful region to be evaluating. If you look at the diviner rock population, there's no, it's a random distribution. There's no unusual rock population associated with Reiner Gamma itself. Okay, so what are lunar swirls? That's what I'm going to try to address, but only the albedo, the optical properties. I'm not going to address the magnetic properties, just the optical properties. And of course, they're high albedo, and the classic understanding of high albedo materials are that you can have compositional differences, Mare, highlands, or you can have fresh and more mature. And you know, we've got this lovely LRO crater that is a classic bright, fresh material. I posit that swirls are neither of the above. There's no topography, but they do have a magnetic anomaly, and it's the magnetic anomaly itself which is a control over the optical properties. That's what I want to convince you of. Okay. I'm going to concentrate not on the head of Reiner Gamma, but part of the southern tail, which really helps looking at the character and distribution of these more carefully. But the properties are seen throughout, not only this swirl, but other swirls as well. Okay, so looking at this particular region, the first thing I want to give you a quick review of is what the classical optical properties are for immature materials as it degrades into mature materials. Looking at a very fresh crater, and the example I'm using here is with M-cube full resolution data, so you get the best characterization of the spectral properties. The crater itself has wonderful pyroxene bands. These are what we love. As you do a traverse with M-cube data from the crater across the rim and into the mature soils, which is what's shown here, you go from this wonderful fresh, immature area grading into the mature. And the classic sequence that people discuss for this maturation effect is that in the visible wavelengths, the materials darken, that these wonderful pyroxene bands weaken, and a combination of both of those gives you the overall red continuum slope of a well-developed mature soil. Okay, if you look at a traverse across one of these swirl area, going from a dark lane into a swirl, avoiding any craters in the swirl, because there are craters scattered throughout, going from the dark lane into the bright albedo, these are the kind of sequence you get. It's brighter, but you notice it's brighter essentially at all wavelengths. Okay, I think I can go on from here. To make sure that this crater that I showed you the example of at high spectral resolution is comparable at the same resolution for the data at this particular swirl, that little crater shown with a green arrow is superimposed on the swirl just to the north of it. So this is a classic example of maturity comparison and the swirl materials themselves. Okay, so at visible wavelengths, you see the properties shown in the 750 nanometer M-cube image. And of course, however, I need to convince you that this character of freshly exposed material is not just at that one crater, but is throughout this region. Namely, if you look at an M-cube image in the middle of the 2-micron pyroxene band, shown at 2200 nanometers, you notice that essentially all the craters, all the immature areas disappear. Why? Because if you compare these spectra, there's an absorption in the immature materials, whereas for the swirls, again, the swirl property is consistent across the region, is maintained. So this distinction between immature surfaces and the surfaces of swirls is fundamental across swirls. Now that we have this high spectral resolution image data, it's quite universal, not just for Rhina gamma, but for the other swirls as well. Okay, so I hope I've convinced you that swirls are not consistent with immature soils. Well, that doesn't answer anything else. We need to find out, well, what are they? Okay, maybe it's particle size. We all know that small particles are brighter than larger particles. Well, we have quite an extensive array of lunar soils where we've done particle size separates. This is the Lunar Soil Characterization Consortium. Show an example here for a basaltic component. And for the Marius soil sequence, it's not consistent with the kind of systematic brightening that we see at swirls. So particle size itself does not let us achieve this character. We've also tried mixing. Well, what if you mix a highland and a Marius soil? That doesn't work. So right now, at least at this point, there's nothing we have that works. The swirls are different. However, and here's where we're going. Let's go back a bit to the early when samples were first returned, and there's a lot of activity done on lunar soils. And it was known, again, that rocks and soils are quite different, and one of the principal species that was seen in soils was these complex agglutinates, multi-component materials. And it was also known that in the glass of these agglutinates, you had small metallic components that were believed to be reducing the FeO to Fe metal, perhaps with interaction with the solar wind hydrogen. And my associate, John Adams and Tom McCord, says, well, okay, since there's these metallic components in these agglutinates, we can separate agglutinates magnetically and then understand what's causing this weathering process on the soil. So they set about looking at a whole sequence of soils and doing magnetic separates. This was in 1973. They're very good data. At that time, most spectrometers did strip charts, and then you had to digitize it. However, they had a modern instrument that gave you punched data on little strip charts that you could digitize. So we do have these digital data. Before I show you a modern version of some of their data, here's two soils that they included in their 73 example. One is an immature soil where the N is non-magnetic, B is the bulk sample, and the M is the magnetic separate. So you have the bulk and then the magnetic and non-magnetic components separated. And you notice for the immature soils, the bulk soil is closer to the non-magnetic component, whereas for the mature soils, which are darker, the bulk soil is closer to the magnetic component. Well, if you translate these into the, this study didn't go much further because at the same time, the community recognized, well, the magnetic component, although it separates components that have these metallic components in it, there are agglutinates that are still in the non-magnetic component. They just don't have the magnetic signatures. So you can't use this technique to separate agglutinates. So they submitted one paper and they didn't come back to it much further. But the data are still here. And here now I've plotted them on the same scale that we have with our swirls. And they have exactly the properties that we want. Namely, the non-magnetic components are brighter systematically. The magnetic components are darker. And depending on which soil you look at in terms of its maturity, the bulk soil will be closer to the non-magnetic or the magnetic. And you can create the characteristics of swirl by simply the variation of the magnetic component, how much the magnetic and non-magnetic component are present on the surface. So you can sort of see where I'm going. Oh, this is another example just to show you that it's not just one sample. Really, the sequence they have are good. There's some data, I admit, of theirs that are too noisy to use, but the bulk shows the same relationship, which is really wonderful sequence. Oh. Okay, so what are swirls? I hope by now you've already formed your own opinion, because what I posit is swirls, the albedo component of the swirls, are magnetically sorted, mature soils. Specifically, as soils mature, we know these agglutinates form, and as these agglutinates cycle and recycle, as Sarah knows, the metallic components get larger. And as you have a well-developed soils, during the normal gardening process on the moon, in a magnetic anomaly, the particles are able to be sorted from magnetic to non-magnetic components. The dark areas contain the magnetic components, the bright areas more the non-magnetic components. That's my conclusion, but these are all the unanswered questions, and I leave these to the magnetic people to answer. It addresses what the optical properties of the swirls are, and it's linked to the magnetic component, but it doesn't answer what the magnetic component is, and where it came from, and how it got there, how deep it is, what shape it is. Okay, you guys have to answer that. Thank you.
Is it possible that we have different origins, and that Reiner Gamma is actually an exception, and that the anapodal location of the other ones help to explain that?
I've looked at, I think, 6 of the swirls, and they all have this characteristics, this albedo relationship, which is quite distinct from the immaturity. I haven't looked at antipode things. That links back to the origin of the magnetic field, and I'm not addressing that. I'm just saying if you have a magnetic field.
And I like your analysis very much. I'm just thinking in terms of the general origin. That there are different ways to create the magnetic anomalies, possibly, and Reiner Gamma is an exception. And the others have something to do with their anapodal position.
Well, okay, that may or may not be true, but Reiner Gamma optically is not an exception.
No, I wouldn't expect it to be. I mean, if you've got a magnetic anomaly, you've got a magnetic anomaly. The question is, what are the origin of the magnetic anomalies? And I have, up until right now, actually been thinking, well, you know, we need to explain them all in the same way, but maybe we don't.
Yeah. Well, one thing, and I think, Ian, you mentioned this, or maybe you did, Megan, that I've looked at some of these magnetic anomalies that don't have a swirl, and I've really, really looked hard for any of these properties, and they're not there. So this directionality aspect clearly is coupled to it too, in some way.
Okay, I think we have time for one more question from Tim.
So you said you've looked at 6 swirls this way, is that right? So do you see any correlation between magnetic field strength and the range of spectral variation?
I can't do that. Clearly, we need to get down close and get close measurements of the actual fields. This particular area, you don't really see in the orbital data because it's too small. But clearly, the features are there. So there's small-scale things that are happening well beyond what is actually measured from our current orbital data.
Okay. Thanks, Carle.